So thanks everybody. I'm giving a talk on exoplanets. I think in the abstract it mentioned, I'll just jump into the agenda slide. I'll cover exoplanets, what they are, why bother, why do we even care about exoplanets or studying them, how do we study them, what can we learn about them. I'll talk a little bit and I'll integrate in, what kind of missions have we done so far, and what progress have we made so far, and what have we learned. And then I'll end with a little bit about what I've been doing personally with regards to exoplanet and actually trying to do exoplanet observing and contributing my data to science, at least hopefully. Professional astronomers one day could use my data for their research, would be ideal. Just a quick mention. So I started really getting into exoplanets, I would say, is about March this year. I've always been interested in exoplanets, but really I took a course through the AAVSO on how to observe them, and that's really where my passion, at least recent passion, has started, and is what prompted me to get really deep into this. And I'm only probably shallow deep. There's so much more that I have to learn, and will continue to learn. But that's what I'm going to try to share with you tonight, is a little bit of what I've learned so far. So before we even get into too deep of things, I wanted to make sure that everybody understood what an exoplanet is. And it's pretty vague general description or definition. A planet outside of our solar system is what an exoplanet is, which is a little bit different than, I think, now I haven't kept up to date with our formal definition of a planet, but there's usually more restrictions or constraints or definition or criteria around a planet in our solar system. An exoplanet is not necessarily so rigid. Exoplanet usually orbits another star in our galaxy, but it doesn't have to. We've actually observed planets that are just what we call rogue planets, out there floating around, wandering through space with no star that they appear to be orbiting around. And so those are very mysterious and intriguing, because we're wondering, where did they come from? How did they form? Did they at least at one point, at one time? Can I make sure everybody's on mute, please? So those are really interesting, because we want to understand, where do they come from, or did they at least one time orbit a star and maybe got ejected by some means. Likely there are more exoplanets than there are stars in the universe, and I think that's probably a soft statement. It's probably, you can probably say it more affirmatively, that there are more exoplanets than stars. We don't have, I think, proof of that, but it's looking more and more so that that's a true statement. And most of the exoplanets that we've detected so far are only within a few thousand light years of Earth, and that's mainly, I think, a technical limitation. It's not that they aren't there beyond that threshold, it's just that that's within the limit of our ability right now. So why do we want to study exoplanets, or what can we gain from it? Well, the first one is pretty obvious. Actually, all of these are obvious. That sheer curiosity of just wanting to know what else is out there. It's what I would consider our modern day version of exploration, of our Lewis and Clark, or we're looking out in the universe just to see what else is out there. Of course, many of the reasons of what we do, or at least NASA likes to tout this one because it keeps funding coming in, is the search for life. Certainly we want to understand if there's another Earth out there, or Earth-like planet where life could form, and just answer that never-ending question that we've always wanted, is, are we alone? Another reason is just to understand the physics of how planets form, how they came about, where did they come about, or where did they come from, when did they come from. So just from a physics perspective, just understanding that how they form is another reason why we might want to study exoplanets. And then the last one is, again, kind of obvious, you've heard it before, is to advance technology. Being able to observe and detect either directly or indirectly these exoplanets is continuing to push us into new levels, and to new resolution, or levels of where we're trying to detect these very, very faint signals. And so it pushes and advances our technology, and those advances can often be used elsewhere to support other things that we could benefit from. So those are just some reasons. It's not obviously all the reasons, but it's definitely a good list of why I think we need to continue exploring and studying these exoplanets. I mentioned, how do we find these things? I mentioned directly and indirectly. This is not an exhaustive list, but it's the list that I'm going to cover tonight, and attempt to try to inform you on how these techniques or methods work. But the first one is again fairly obvious. How do you find an exoplanet? Well, if you point your telescope at it, you take a picture, you look for little white dots maybe that are going around the star. And you'll see here that that's not so easy. It's not impossible, but it's not very easy. The other methods are indirect methods, and by that, what I mean is we monitor properties of the star, whether it be its position, the brightness of the star, or the color or the spectrum of the star. And based on how that changes over time, we can infer that there is, or there must be, a planet orbiting around that star. And those are the methods that I'm going to cover: astrometry, photometry, otherwise known as the transit method, and radial velocity, which is also commonly called the Doppler shift method. And so we're going to get into these methods here in a bit. Before I jump into those, though, I just wanted to kind of give you a perspective of what have we found so far and by what method. This is off of the NASA exoplanet dashboard, which you can check in, daily, because it does get updated as soon as they find new exoplanets that are confirmed and or new candidates. You can see the numbers that we have up there, 4,500 plus confirmed exoplanets since we started tracking this. But by far, the transit method or the photometry method has been the most successful so far, followed by radial velocity and then microlensing imaging, and it really drops off. Notice the one that I am going to talk about briefly is astrometry. It really hasn't been that fruitful, and I'll get into the reasons why. But it is very low on the list on the number of exoplanets that we've actually discovered using that technique. Of those 4,500, this is a breakdown of what we think or believe the size and composition of the planets to be. You can see almost about half of them are Neptune or gas giant sized. About 1,400 or so are classified as what we call super Earths, and that's not to be confused with them being Earth-like planets. It just means super Earth is a term that we use to describe the size of a planet, or exoplanet in this case. Super Earth, I believe, if I remember right, is defined as anything that's twice the size of the Earth up to 10 times the size of the Earth. And so that range of sizes is what defines a super Earth. And then you can see there's a handful of terrestrial and then even unknown planets. We've detected some planets orbiting stars, and we're not quite sure yet what their composition is or density, so that we could infer whether or not they're more towards the gas or more towards the terrestrial. So here I'll walk us through the different methods, and let's start with the easiest one, the direct imaging. I mentioned earlier, you basically point your telescope at a star, take a picture, and see if you can see the exoplanets going around. And while that is very easy, the issues with that, or the challenges with that, is that our atmosphere scatters the bright starlight, and it looks like the image that you're seeing here. And so when you're trying to see if there are planets orbiting around that star, they are much more difficult to see because they're so much fainter than the star. It also doesn't help that most of the exoplanets, relatively speaking, are close to the star, and so they're all blinded by this bright starlight. And it's like, you know, the analogy is you're trying to see a firefly buzz around a bright lighthouse, and who knows from how far, you know, thousands of miles away. So how do we do this then? How do we? I mentioned just previously that it's difficult, but it's not impossible. And actually, there are. I'll walk you through a couple examples where we've been successful for this. So how do we do that? Well, they still take an image of the star, but they use one of many techniques to either mathematically or through by some means subtract out the starlight, leaving behind only the exoplanets that are orbiting around. And so here is an image of, I think it's HR 8799 system. And this is a Hubble Space Telescope image, and it's exactly what you would expect, is just the blurry blob of starlight blinding what we thought or believed were exoplanets revolving around. And it turns out, after a little bit of further processing, that image on the left turned into the image in the middle. And so they were able to subtract out the starlight, leaving behind these little dots. And if you look at the image on the right, that is what we believe to be the size of the orbits of those exoplanets going around in their position. You can see in the lower right-hand corner, to give you a little perspective of how large these orbits are around that star, is they give you the comparison or relative size of Neptune. And you can see, I think if I put it up there, I think all but only one of the three is even close to Neptune. The rest are much further out than that. And so these planets are very, very large, and they're very, very far away from their star, which helps with the direct imaging technique. Later on, after that Hubble Space Telescope image was taken, the Keck telescope pointed over there and also imaged this same planetary system. And you can see they also subtracted out the starlight. And in this case, they were able to capture a fourth planet that wasn't visible in the previous image. So there's actually suspected 4 planets revolving around this star. And then this, the data here that's showing is this is a projection of the next 10 years where they believe that these exoplanets will orbit to. And so it'll be very interesting year over year to take pictures of this same planetary system and show that animation. It'll be really exciting to see that. I think one last, no, this isn't, I got one more after this. So there's one more example here. Just in April of this year, the Young Suns Exoplanet Survey also was able to image an exoplanet with direct imaging through similar techniques. You can see here that this is a star that's 360 light years away, and this is a very large exoplanet, 6 times more massive than Jupiter, and is again very, very far away from the star, which helps with this method, being able to detect it. And then finally, one more example, just in July of this year, using SPHERE on ESO's very large telescope, they were able to directly image some exoplanets here. Again, that inner one is 14 times the size of Jupiter at 160 AU, so that's really far out there. And then even further is one that's 6 times the size of Jupiter, 320 AU out there. So again, most of what we have, the success that we've had with direct imaging has been because the planets that we're seeing are extremely large, and they're very, very far away, which helps with the blinding light that the starlight usually disguises these exoplanets. So that was the direct imaging technique. The next one is the astrometry technique, where you may have heard where we watch a star and we watch the physical properties of the star, in this case, the position of the star, and we watch for a wobble. So I've got a little animation here. Hopefully this does well over Zoom that you can see. But when a star, or rather an exoplanet orbits around a star, it's actually orbiting around a center of mass. So the sun, or in this case, the star, and the planet is the system, and it orbits around the center of mass. And what it does is it's actually making the star wobble ever so slightly. And we monitor the position of that star relative to the other background stars that you saw there over time until we see that motion repeat. Now, the period or the duration that it would wobble from one extreme to the other extreme depends on the period of the exoplanet, the time it takes to go around the orbit. Some are very, very quick, which you'll see later on. A lot of the exoplanets that I'm imaging go around their host star in days, 3, 4, 5 days. And so it's very, very quick. And the effect of the amount of wobble, the shift that we see in position, is also dependent on the mass of the planet and the mass of the star. And I have an equation here I'll attempt to walk you through to demonstrate that effect. So I wanted to just ask real quick, just to give a little bit of perspective of how small this shift in position really is. If you take, for example, the Alpha Centauri star system, which is the star closest to us, and you looked back at the sun and you watched the sun for a period of 12 years, which is the time that it takes Jupiter, our biggest planet that has the biggest effect on our sun's wobble, if you watched it for 12 years, how much would the sun, from the perspective of Alpha Centauri, shift in the night sky? And I'm looking for an answer in terms of arc seconds. Is there any guesses? No guesses. All right, I'll jump to the punchline here. So it is 3.7 milliarc seconds. So that is incredibly small. If those of us that image with our telescopes, we usually image on a scale of 1 arc second. This is 3.7 milliarc seconds, which is incredibly small. And our best technology today can detect that. We can detect to a resolution of about 1 milliarc second. But now you got to remember this hypothetical scenario where I said we were on Alpha Centauri looking back at the sun. That's the closest star. When the stars get even further and further away, that effect goes down. And so that's one of the other major challenges or disadvantages of this technique, is that it's really only useful for nearby stars up to about 200 light years away from us. I'll get into a little bit more on Gaia, but I wanted to mention here is that you may have heard of ESA's Gaia mission, which was launched back in 2013. It's currently creating a 3D map of the Milky Way, and it's expected to reveal thousands of exoplanets. The equation for that shift is shown here. And so that shift, milliarc seconds, if you're not familiar, is actually an angle. And so that's what theta there represents. It is a factor of A, which is the from Earth to that star times the ratio of the mass of the planet to the mass of the star. And the interesting thing about this method is we can experimentally measure the shift, right, what I just mentioned. The D, the distance to the star, can be determined through one of several methods. But if we didn't know, Gaia Mission is actually, that's what it's doing right now, is it's measuring all the Ds to all these stars, A can be calculated if we know the period, right? So if we watch this star long enough and watch that wobble and we figure out what the period of that wobble is, you can calculate A, which is the orbital distance, through Kepler's third law. And then the mass of the star is also something that we can easily estimate through various techniques. And so where I'm going with this is that you can actually solve for the mass of the planet. And this is what the astronomers do, is they measure the effect of this shift due to the wobble, and they can figure out the other quantities, and they can figure out what the mass of the planet must be. Now, in the case of multi-planet systems, which we don't know if it's one or many, but it would be the combined effect of the mass that we would reveal. So that is the astrometry method. Now we'll move on to the radial velocity method, which is also an indirect method. This one differs just a little bit because the astrometry method that I just mentioned measures the lateral shift, either the side to side, up to down, left to right, lateral motion, whereas this radial velocity method is actually measuring or detecting the motion of the star to and from us, so along the line of sight. And we do this using Doppler shift and the fact that the star's color has a spectrum, or the spectrum of the star has this unique fingerprint that is all these dark spectral lines, right? I think most of us are familiar with this. And so what they're doing is they're monitoring the spectrum over time, and they're looking for minor tiny little shifts in the spectrum, either towards the red side of the spectrum or towards the blue. And I have a little animation here that should help convey this. And so as we zoom in and we're looking, and now you see the star is moving away from us, and it's a redder spectrum. It's coming around, and now it's moving towards us. And so it presents a more compressed blue wave-like pattern. And so we can measure that difference. And based on that, we can calculate the velocity of the star. And again, remember that this is only the to and from motion that we're measuring. This technique is blind to the lateral motion. The lateral motion is something that we detect through the astrometry method, which I just previously mentioned. The challenges with this is that, well, actually, let me just show you the formula here. So the radial velocity, again, that's that shift that I was just mentioning. We experimentally find that. A, again, can be calculated from Kepler's third law, where once we know the period and the mass of the star, you can easily calculate A, which is the orbital distance of the planet. P, again, comes along with our observations. And then again, M is the mass of the star, which we can easily estimate. That leaves M sine I. And so this sine I is the annoying part. I mentioned before that all this method does is it measures the component that is along the line of sight, the velocity that changes along the line of sight. So if it's orbiting, it is in fact orbiting in all three dimensions, we can only detect through this method the component that is along the line of sight. And that's what this sine I term is trying to isolate. I stands for the inclination angle, and I've got a little image here that helps visualize this. So if we're looking along the line of sight, if that inclination angle is such that the orbital axis is exactly 90 degrees, which would produce the maximum amount of wobble to and from to the observer, that would be the sine of 90, which is 1, which is the maximum amount of wobble that you would detect. If it's anything less than that, say 45 degrees or even 0, if it was 0, you would have a sine of 0, and you would not be able to detect it at all. That's what I meant by it being invisible. But if it's anything less than that, it would be, you'd only see the component again along the line of sight. And so what does that mean? That means that really we can only infer this quantity m sine I. We don't actually know what the inclination angle is through this method. And so it's annoying that we can't really truly know what the mass of the planet is. But the good thing is that sine is always going to be a number that varies between 0 and 1. So what we can say with certainty is that whatever this quantity is, m sine I, is that it's the minimum planet mass. It may be larger than that quantity, but we can say that it can't be smaller. So just to recap, the astrometry method that I mentioned before measures lateral motion and can derive the mass of the planet, whereas this one measures the to and fro motion, but can only really understand the minimum planet mass. The last method is the photometry method, and otherwise known as transit detection. And this is what I'll talk about here later, is what I'm currently doing with my own telescope. It has its challenges, which I'll walk through, but in terms of complexity or being able to detect it, the other amount of shift in the astrometry, or the being able to detect the shift in the spectral lines, those are, beyond average astronomer equipment. You need professional equipment with, very high quality instruments to detect that. Comparatively, the transit detection can be done with very, amateur equipment, which is why it's probably been the most successful out of all the methods that I mentioned, because it is so easy, and the amount of that you're trying to detect is actually achievable, and it's not this insurmountable task to be able to measure that shift. So what is the transit? It is where we watch that same star over a long period of time, and we monitor the brightness of the star. And we watch until, hopefully, an exoplanet will pass in front of that star, blocking an ever so small amount of its light. And that brightness that we're monitoring will actually have a little dip in it until the planet then stops transiting and goes back, around behind it, and it returns back to its normal brightness. And that's essentially how we measure the dip in light, or detect the planet going in front. Now, what's the problem with this method is that it only works for planets whose orbits are oriented such that they actually do pass in front of the star, that they eclipse the star from our perspective. And if you, and please don't ask me to explain this, but this is something that I was reading in preparation for this talk, is when you want to try to estimate what is the probability of, from any random location that there's other stars that will have exoplanets orbiting across the face of the star from your perspective, it ends up being a probability of R star over A, where R star is the radius of the star, and A is, again, that orbital distance of the exoplanet that you're trying to detect. And it makes sense, right? For bigger radius stars, bigger, giant, more stars, the probability that you'll be able to detect a transit is higher. Comparatively, at further and further away planets orbiting their star, so larger A, the probability will be much lower. And if you're wondering, for the Sun and Jupiter system, if you plug in those numbers, the probability ends up being a little bit less than 1 in 1,000, which is not very good. It's better than winning the lottery, certainly, but it's still not that great. So what that means is that there's a lot of exoplanets that are orbiting stars that we'll never be able to detect using the transit detection. The other challenge with this technique is that you have to be there when the transit happens. Long period planets, so ones that are very far away from their star, right? You have to monitor them for a long, long time until they transit across the face of that star, and that could be just a very tiny portion of the overall period of that star, or of the exoplanet rather. To further complicate this, unless it's a huge planet, you're trying to detect small planets, the dip in light is even smaller. And so now you're starting to get into the area where the percent of dip in brightness is becoming more and more difficult to discern between the noise of your signal. I have an example here, just to give you, if we revisit our example of the Alpha Centauri system, if you were on Alpha Centauri, you were looking back at the sun, and you were only looking for when Jupiter transits across the face of the sun. First, you'd have to monitor the sun for 12 consecutive years, Earth years, that is. And when Jupiter does indeed go in front of the sun, it would produce about a 1% drop in brightness, which is easily detectable with amateur equipment. The problem is that it only transits across the face of the sun in 12 hours. And so out of that 12 years that you would watch the sun, you'd have to be there for those 12 hours that it was transiting across to be able to detect it. And this is the issue with us doing this from the ground and observing transits from the ground, is at least a portion of our day, the sun is out, right? So we can't see the stars well enough to be able to monitor transits when the sun is out. And then if you live here in Wisconsin, the other half of the times it's cloudy. So it makes it very difficult, that you have to be able to be in the right place in the right time if you're trying to do these observations from the ground. And which is why you'll see a lot of the missions that are doing this transit detection now are space-based telescopes. Again, keeping along with the math, for those that are inclined, if you wanted to understand the relationship between that fraction of blocked light, so the change in brightness relative to the original brightness of the star, it's equal to the relationship of the radius of the planet to the radius of the star. So it's more or less the area of the planet and related to the area of the star that it's blocking. And so that's what that relationship eventually reduces down to. And so here, once we understand that, if we know the radius of the star, we can again infer the planet's size. And of course, we can get the period by multiple observations. So I wanted to take a minute just to mention the Kepler Space Telescope. I mentioned that we would talk a little bit about progress so far in missions that we've been on. The Kepler Space Telescope is a mission that launched in 2009. It was active for 9 years. It's now since retired because it's ran out of fuel. But it was very successful in that it detected thousands of exoplanets. It was designed to do exactly what I had mentioned, is stare at a patch of sky for a long, long period of time and just monitor And I believe that the Kepler Space Telescope was targeting Earth-size and smaller planets that were ideally in the habitable zone. Again, to support that the why of is there life on other planets. This is the patch of sky that Kepler looked at. It's just a little bit above Cygnus, if you're familiar with where that constellation is located. And you can see all those little squares are the different array of sensors that it has as detectors. And so it's good looking at a fairly decent patch of sky. The issue that came up with Kepler is that I think of maybe 3 or 4 years in, actually maybe even 1 year or 2 years in, it has four reaction wheels, which are needed to control the pointing accuracy, to be able to stay while it's orbiting around, stay pointed at that same patch of sky. Well, shortly into the mission, it lost one of those 4 reaction wheels. Well, okay, that was okay because they had 4 in there as a backup. You really only need 3 to properly control the orientation and pointing of the telescope. But then I think around 4 years in, a second one was lost. And now they lost the ability to accurately point the Kepler telescope in that patch of sky. So they thought about it, and they realized later on that using the symmetry of the telescope and the solar wind pressure, they could point the scope, depending on where it was in its orbit, to a patch of sky and monitor it for at least about 80 days until they would then, have too much of a torque because of the solar wind, and they'd have to reorient the other reaction wheels and point the telescope into another direction. But because of this, the mission didn't end in 2014. It continued on, I think, for another 4 years or so, and continued to be very successful. The second portion of that mission was termed K2, and this visual kind of represents where it looked on the sky. Rather than looking at just that one patch of the sky, it then now had to evolve, like I said, every 80 days along the line of the ecliptic. And so they were able to still continue and do research, even though it wasn't maybe as intended. Other missions, some of these which I'll mention, but I wanted to show this graphic. I thought it was really neat that kind of showed the timeline. Ground-based observatories is where a lot of things start, and that is no exception here with exoplanets. But Hubble did do some early exoplanet, even though it really wasn't, suited for, or really it wasn't it's not the greatest telescope to do this kind of research. And then these other telescopes along the bottom here, some of which haven't launched yet, James Webb, which Dennis is going to talk about next month, all had at least some ability to do some type of exoplanet research or contribution to exoplanet hunting. The ones on the top, however, are dedicated exoplanet missions. And Kepler is one I just mentioned. I'll talk briefly about TESS as well. But these other ones, see these other ones in the future, Plato and Ariel, and there's actually one that's not depicted here, which is the Nancy Grace Roman telescope. It would belong on the bottom here. That's going to launch, I believe, in 2025. So I mentioned the Gaia Mission. Here's a little bit more information about the Gaia Mission. It was launched in 2013. It's still going as we speak today. And its mission is to make the largest, most precise 3D map of the Milky Way. It was originally a 5-year mission, and now it's been extended to 2025 because of its success. And this is where I think it's very incredible that what it's doing is it's measuring the brightness, the spectrum, and the precise position of about 1 billion stars. And it's doing this 70 times over 5 years, which equates to about 1% of the Milky Way. And the precision that it's doing this is just incredible. Click this video just so you can mute it here so you can see some of the animation of the Gaia space probe. But the precision is down to around 10 to 24 micro arc seconds. So if you remember in the other techniques, I mentioned that the shift in position was 3.7 milliarc seconds. This is more than adequate, or will more than adequately be able to measure those, and then much beyond that, stars in more distance, which is why this data as it comes in is being used to help define all those Ds, the distances to the star, to inform those other calculations that I showed you. So this animation just shows now how it's mapping the sky. Hopefully that's coming across well. So in any case, the data that Gaia is collecting, again, its primary purpose is to create this 3D map, but it's expected to discover thousands of exoplanets in doing while it's doing that. Another mission is the Transiting Exoplanet Survey Satellite. Again, this is one that is dedicated to exoplanet research. Launched in 2018, and it's still going. It was originally just supposed to be a 2-year mission, and they extended it, I think, for another 2 years. They're basically just going to repeat what the first 2 years did. And what it's doing is it's surveying around 200,000 of the brightest and nearest stars, looking for exoplanets or transiting exoplanets. The good thing is that because it's looking at the brighter stars means that us amateurs can do ground-based follow-up observations. And that's exactly what people are doing. And I'll show you later here in the stuff that I'm doing is that there's these things called test objects of interest, TOIs, that are those candidates that they think may be exoplanets, and they want the amateur community to do follow-up observations and submit their data. Some other fun facts about the TESS space probe is that the cameras have an image scale of 21 arc seconds per pixel, which is pretty low. The detectors are sensitive in the blue to the near infrared, and TESS aims for 50 parts per million photometric precision on stars with a magnitude between 9 and 15, although brighter stars can be monitored. So just an incredible instrument here. So I have a quick animation here too, which so hopefully that came across the Zoom while I did tried to edit this video down just so it pointed out those key points. But in case you missed it, what I thought was cool is as it's orbiting, I think it's every 14 days, I believe. So it completes an orbit, and so every time it comes around, it's storing that data on board. It's actually doing some calibration of the image data on board, and then when it comes to zoom past Earth again, it spends that time sending the data back to Earth, wiping its drives clean so that it can go around again for another observation. And I can't remember how many cycles it's on now. I think maybe 85. It's currently on the 85th orbit rotation right now. But you can see the north or southern hemisphere first, I think, and then the northern or vice versa. And so when the mission got extended, it basically is just going to repeat that. So it's done one full recording of the north and south hemisphere, all sectors, and the mission, when it got extended, is just to repeat that. This is just a quick video to show you some of the things that they're now doing with that data. And they're using it in combination with some of the data that they get from some of these other missions that I mentioned, Gaia specifically. So this is a representation of all the stars that TESS has observed. Those are the two hemispheres and the different sectors that I talked about. And then they paired that data with all the Ds, the distances to the stars, to create this three-dimensional map. And what's mind-blowing to me is that as impressive as this is, it zooms out here a little bit, and it just shows you that we're only looking at just a tiny portion of our entire Milky Way, because this is where about we're located, and that's the neighborhood that we're looking at. This is the center of our galaxy over here, the Milky Way. And so we're still, even as impressive as this is, it's really only looking at the nearby neighborhood. So we've got a lot to still explore beyond that. For the interest of time, there are tons of missions and more details that I can get into, but I would encourage you, if you want to know more about other missions or upcoming missions, certainly look into what was formerly known as WFIRST and has now been renamed the Nancy Grace Roman Space Telescope. It is also going to be contributing to exoplanet science in that it has a Hubble field of view, or rather it's a field of view 100 times that of Hubble. It will have a coronagraph, so it'll be able to block out that bright starlight. And then I think its primary method, which I didn't cover here because quite frankly, I'm not ready at this stage to articulate or describe that technique, but gravitational microlensing is another exoplanet detection method, and it will use that method as its way to find additional planets, exoplanets. The other one is James Webb. Again, not to steal Dennis's thunder next month, so I didn't want to go into any detail here, but Webb is going to definitely contribute to exoplanet research and be a more detailed look at hopefully the atmospheres of these planets. And so we can start to learn more than just, you know, the size, the mass of these, but actually start to get composition of not only the planet itself, but also its atmosphere. So what have we found so far? Honestly, I struggled with this, and I basically boiled it down to just this one slide, and I don't go into too much detail because this could be a lecture in itself, and maybe I will do a follow-up lecture. But we found a lot. One of the interesting things that I think is neat, that of all the exoplanets that we're finding and we're observing and learning about, we found that the gaseous giant planets in our own solar system seem to be misplaced. Most of what we're finding, or at least let me say, most of what we're being able to detect, are giant gaseous-like planets very close to their host star. We call them hot Jupiters. And we are not, I mean, other than the few examples that I mentioned in the direct imaging, it's not all that abundant that we have these gas giant planets far away from their stars. So I thought that was a unique thing. Obviously, as we continue to do this, we have more and more evidence for how planets form. We're seeing planet formation in the different phases and supporting the theories that we have along with that. We found compact multi-planet systems. We found planets that are circling more than one star. We found extremely hot Jupiters called lava worlds that are just absolutely incredibly close to their star, that it literally potentially rains lava rock on those planets. And then, of course, we found Earth-like planets. We found planets orbiting dwarf stars, giant stars. And what's to come is hopefully understanding more about these exoplanet atmospheres. And who knows, as technology gets better, maybe we can actually start to detect moons around these exoplanets that are going around stars outside of our own solar system. So I mentioned since about March, I've been really getting into trying to do my own transit detection, and I have been successful. I've shared some of my results with some of you since then, and I've done it a couple times now to the point where I think I'm getting good at it and I can do it repeatably. But I think for me, my next steps are to now get a deeper understanding of what it is I'm actually doing. I'm physically doing it because I'm doing what I was told or what I was taught, and I want to get a little bit more into what it is I'm recording, and what can I do with it. But NASA, ESA, all these professional astronomy organizations heavily rely on amateurs to help do ground-based follow-up. And so this is part of their strategy, that it starts with ground-based observations, and then based on that, those can become candidates for these higher level levels of research. Because, you know, to get time on the Gaia, or rather the other missions that I mentioned, is not cheap, and there's a list of people lined up to try to get time on those telescopes. So to build the case, they're heavily relying on ground-based telescopes data. This is just an image of my setup that I use. It's a 11-inch Celestron Schmidt-Cassegrain telescope, and I have a CCD QSI 690 camera on there, and then of course I have a focuser and a filter wheel. I do all my exoplanet measurements using a V filter, which is filters for a specific range of wavelengths. It's a scientific filter so that my data can be used and compared with other data sets done by other astronomers. It's not required that you use that filter. You can detect it without any filter at all. It's just because I'm choosing to share my research, I want it to be able to be useful to others, so I do use that filter. And this is just an example of one of the transit curves that I observed. This was a exoplanet called TRES 3b, and you can see this first plot of data is the raw data plotted relative brightness. So if you remember from the transit formula, it is the change in brightness relative to the original brightness of the star. So this is the original brightness, a factor of 1. It dips down to about, whatever that is, like 3% or so, and then goes back up. And this was, I can't remember exactly, but this was over a period of maybe 2 hours, is what the transit actually took. So I always start my imaging session well ahead of that, 30 to 45 minutes before the transit is expected to occur. That way I don't miss it. And then I always image 30 or 45 minutes after the exoplanet transit is expected to end. That way I catch it all. And what these other curves here are, especially these right here, are stars that I'm also monitoring the brightness of in the same image. And I'm comparing that against the star that I'm interested in. And notice that these don't have any dip in light. And so that's my control group. I'm showing that this is not an anomaly. It really is a dip in light, because these other stars stayed constant. So that's I didn't want to go too much into detail more than that on the stuff that I'm doing, because I did give a talk 2 weeks ago that got a little bit more into the technical how I'm doing that. So if you're interested in knowing more about that, I can share that PowerPoint presentation. Unfortunately, I think Thomas, I think if I remember right, there was a technical issue and that recording was not able to be kept, I believe. But nevertheless, I can share the PowerPoint slide deck from that, and you can always reach out to me if you're interested in more of that and you didn't get a chance to catch that. If you yourself wanted to get more into this and wanted to contribute to science, you certainly, if you have your own telescope set up, it doesn't have to be a 11-inch. I think there's amateurs out there with 8 inches telescopes. And very meager equipment that you can do this yourself as well, and contribute to science. There's a program called Exoplanet Watch, which NASA hosts, and you can go on their website. The link is at the top there, and every night by time zone, they give you suggested candidate targets that you can observe for the night. So if it's clear out and you're available and free, and it's at a reasonable hour where you're not losing too much sleep, you can set up your telescope and capture these transits and submit your data to science. And if you don't have a telescope, but you still want to participate, the other program that I heard about is this Planet Hunters TESS. So I mentioned the TESS telescope and all the data that it's collecting. Well, they need help analyzing that data. And so it's free, you can participate in doing this. Go to this Planet Hunters TESS website, register, and it walks you through it. It's very simple, and what they're basically asking you to do is help identify where transits occur, so that then that eliminates having to process all the data where transits aren't occurring. It really cuts down on the amount of processing that has to happen for their supercomputers. And so if you want to contribute that way, you can certainly, in your free time, help identify where the transits are occurring. In fact, there was an article as I was reading this not that long ago. A father and son actually helped identify a new discovery exoplanet by doing just that. So certainly many ways for you to participate. So that kind of rounds out what I wanted to talk about. Talked a little bit about what exoplanets are, the different methods that we use to detect them, a little bit about the various missions that have happened so far and are upcoming, and then how we can all contribute to science if you so choose. That is basically my presentation, so I'll open it up for questions.